Okay guys, so let's actually get into what implicit differentiation looks like. So the idea here is that we've been working with explicit functions. They were written very clearly and explicitly so that you could see that it was a function of x. It was solved for the f of x or the y. What we want to look at is functions, well, either functions that just aren't written in that explicit form or things that aren't functions at all. So there's perfectly legitimate relations, like x squared plus y squared equals 1 is the unit circle. And we should be able to talk about slopes or tangent lines, but our current techniques of taking derivatives don't do a great job of that. We could do it with the circle, but we could quickly come up with things where they don't work. So let's just start off with an example. So let's say I have xy plus x plus y equals 5. And my goal is to find dy dx. So I want a formula that tells me how fast y is changing with respect to x. And it could just as easily be that I want to know how fast x is changing with respect to y, but the notation tells me. So really pay attention to your notation. You'll see a lot of dy dx, but it doesn't really have to be that. As soon as I see this, this tells me that my variable is x. So whenever I see a plain old x, that's just my variable, whereas I'm thinking of y as somehow being dependent on x. So y is like the function, it's like the f of x part of this. Okay, so if I want to find dy dx, this is like the way I figured out the derivatives for the inverse function. So the new way would be to take the derivative of both sides with respect to x. And the right-hand side here is really easy. The derivative of 5 is 0. The left-hand side we have to be really thoughtful about. So the first one is a product of x and some function. So we're thinking about y is like an f of x. So we're going to say this is a product. We're going to do y times the derivative of x with respect to x, which is just 1. And then we're going to do x times the derivative of y with respect to x. And then, okay, so there's our product rule. We also need to take the derivative of x, which is 1, and the derivative of y, which is dy dx. Okay, so for this section where we're just working with x's and y's, you have my permission to use y prime, so I'm okay with this. But just heads up that in the next section, we're going to get an extra variable in the mix, and in that case, I want you to very clearly tell me what you're taking the derivative with respect to. So remember that our goal was to find dy dx, and which is this y prime. So at this point, we can just solve for it. It's just an equation. So we do our derivative work, and then we just go back to the algebra problem. Can you solve for y prime? So you'll want to isolate the y primes on one side. They're already on the same side, so let's just get rid of the negative 1 and get rid of the 1 and the y. Subtract 1, subtract y. And then you can factor out a y prime if needed, if there's more than 1. And then you can divide. Sort of getting to the bottom, negative 1 minus y over x plus 1. Okay, so what's kind of interesting here, dy dx equals, is that this derivative means exactly what it used to. It means I have some curve defined by the equation xy plus x plus y equals 5, and I now have a formula that tells me the slopes of the tangents to that curve. What's new about this formula is that to find a slope, you actually have to know the x and the y coordinate of a point. So if I told you that this thing went through the point 1, 1, I don't know that it does. In fact, I'm pretty sure it doesn't. It goes through 1. No. If it went through 1, 1, you would plug in 1 for x and 1 for y, and that would tell you a slope. Okay, so this is the new way, and I get this formula, and okay, it's different, whatever. I would like to compare with the old way. The old way would be that we wouldn't go trying to take the derivative unless we had it solved for y. So kind of what happens is we do the solve work up front. So I'm going to go ahead and isolate the y's. I'm going to say I have an xy plus y equals 5 minus x. So subtract x from both sides, and then factor out a y. And then then divide by the x plus 1. So it turns out that this is a rational function. And I just want to point out right now, this worked beautifully here, so we'll actually be able to see if we get the same answer, but you can't, unless it really is a function, and even sometimes when it is a function, you can't solve for y all the time. You cannot just expect that this will be doable. So we really do need implicit differentiation, even if sometimes we could get away with not doing it. So now, if I want to dy dx, I just go ahead. You really are taking the derivative of both sides, but it looks a little more boring when there's just a y here. And I apply my quotient rule. So I have the bottom. The derivative of the top is just a minus 1, so I'm just going to stick a minus out in front. Minus the top, and then the derivative of the bottom is just 1. And that's all over x plus 1 squared, which is going to give me negative x minus 1 minus 5 plus x over x plus 1 squared. And then the x's drop out, minus x plus x, and I get a negative 6 over x plus 1 squared. Okay. So here's my concern. That doesn't look like what I got the other way, and I'm claiming this does exactly the same thing, tells you slopes of tangent lines. So the big difference that's bothering me is, for starters, this one has a y and this one doesn't. Also, this one doesn't have the square in the bottom. But the y thing actually solves our whole issue for us. We don't have a y over here because we figured out y in terms of x, so we can actually take advantage and say, well, we know that y is really the same as 5 minus x over x plus 1. So we could rewrite this if we want to, not necessary if you're just doing implicit, but to check. We could say this is negative 1 minus a 5 minus x over x plus 1 divided by x plus 1. And it still doesn't quite look the same. So let's go ahead and multiply top and bottom by x plus 1. So we're going to get this negative 1 multiplied by the x plus 1. We have to make sure we distribute. And then here, the x plus 1's will cancel, but we'll be left with the minus sign, and that has to distribute to the 5 minus x. A fraction bar groups those, so they're really implied parentheses there. And this is looking good because there's our x plus 1 squared on the bottom. Okay, so now we have a negative x minus 1 minus 5 plus x. This is starting to seem familiar. Squared, that's exactly what we had up here. So we should, in fact, end up with exactly what we had before. So they really are the same. Implicit differentiation will give you the same correct answer, but it might look a little bit different. Okay, I think I'm going to sneak one more example in this video, except I used a paper, and then you'll be able to try some on your own if you'd like on the next video. So let's say we have a y squared plus x ln y equals ln x, and we want to find dy dx. Okay, so again, this should really give you a clue as to what's a function and what's a variable. So y is supposed to be like the function, the more than just a variable, and x is just a plain old variable. So we're going to take derivatives with respect to x of both sides. Okay, so the derivative of a y squared with respect to x is going to be a 2y, and then here's the tricky part. Because we're thinking of y as being somehow dependent on x, not just a variable, we're always going to get a chain rule every single time we take the derivative of something with the y. So this is like function squared, and the derivative of a function squared is 2 times the function times the derivative of the function. And again, you can use the dy dx or the y prime. I leave it up to you. dy dx is sometimes easier to spot, but y prime is easier to write. Okay, and then we have an x times the natural log of y, so that's going to be a little product rule. We're going to have the natural log of y, derivative of x with respect to x is 1, and then we'll have an x, and then the derivative of natural log of y is a 1 over y, and once again you'll have that chain rule. Derivative of natural log of a function is 1 over the function times the derivative of the function. And I'm just going to get tricky and mush that all together. And then that should equal the derivative with respect to x of the natural log of x. So that's just a 1 over x. No chain rule there. That really is just natural log of our variable. And then we're back to where we were before. We need to isolate the y primes. So let's see. I'm going to move this natural log of y over. I see a 2y y prime plus, I don't know, I mushed that together, but actually I think I prefer x over y times y prime. You can always kind of mush fractions around however you want. So you can move the x up in the top, you can move the y prime down from the top. All of that is legal. And then I have a 1 over x minus the natural log of y. I'm going to go ahead and factor out my y prime, although I would point out at some point you're going to have to clear the extra fractions. So if you wanted to do that now, you could. I'll go ahead and do it in the last step. Okay. And then I divide, so I get my y prime, I'll go ahead and rewrite it as dy dx since I'm close to the end, is equal to 1 over x minus the natural log of y divided by 2y plus x over y. So this is solved, but the answer is not simplified. So my last step here would be, I want to get rid of that x and that y, so let's multiply top and bottom by xy. Make sure you distribute. So on the top, xy times 1 over x is just going to leave me with a y. And then nothing cancels here, so I get minus xy natural log y. And that's going to be divided by 2xy squared. Nothing cancels there. And then here, a y cancels, but I'm left with an x squared. And that looks like